So far we have seen that you can generate all kinds of limits using limits of only certain shapes. Yeah, those certain shapes which are very important are arbitrary small products and equalizers. And if you want to obtain all finite limit as in the shape of the diagram is finite, then you can do all finite products and equalizers. Yeah? And there is another way of doing the same thing, like if you have the terminal object and pullbacks, then also you have got all finite limits. Now tell me something about real numbers. If real numbers have got all limits, I mean rational numbers don't have limits of its sequences, correct? But real numbers do have limits of convergent sequences, Cauchy sequences, let me be precise. What do we call it because of this property? Complete. So we are going to use the same terminology over here. So let's start writing from this point. So say that a category C is complete if it has all small limits. Okay, all small limits. And finitely complete, yeah, that's another term. Finitely complete, or an alternative is Cartesian. Yeah, we call the category Cartesian if it has all finite limits. So these are some commonly used names. And when do we say that the category is co-complete? Well, obviously you can guess if it has all small co-limits. And it will be also called co-Cartesian. These are just some names. So a category which has all small limits, we call it complete. If you have a partial order, yeah, which has all small limits, then what do you call it? A partial order? Complete order? No, that's not the correct one. So first of all, if it is both Cartesian and co-Cartesian, then we will call it a lattice. Yeah, it's a bounded lattice. So let me just write this for you, that if a poset P less equal is bicartesian means both Cartesian and co-Cartesian, then it is a bounded lattice. Okay, so what are the limits? Tell me. Limits are equalizers and products. Yeah. So finite products are meets. Then equalizers in posets thought of as categories, equalizers don't matter because there are no parallel arrows at all. So therefore you don't need to worry about them. So for Cartesian, you just need to have all meets, finite meets, binary meets, and the terminal as well. Yeah, what is the terminal? Largest element is the terminal object, correct. And similarly, the dual version, that all joins should be present and the minimal element should be present. That's why it's a bounded lattice. Whereas if it is bicomplete, then it is called a bounded I mean, it's automatically bounded because that's in the definition, but it's a bounded complete lattice. Yeah, it's called a complete lattice. So automatically, lattice property is equivalent to having good limits. And completeness also comes from completeness, because arbitrary products are nothing but arbitrary meets, infimum. Yeah. Okay. Now, while we are talking about functions which are, while we are talking about categories which have certain properties, but we don't really stop there. We always have to talk about the maps which preserve all these things. When we are talking about posets, then normally the functors between posets are monotone maps. But functors which preserve limits are called meet-semi-lattice homomorphisms. Functors which preserve finite colimits are called joint semi-lattice homomorphisms. And functors which preserve both are lattice homomorphisms. So basically, we have to talk about functors which behave nicely with respect to limits and colimits. So there are three different ways in which limits and colimits can interact with each other, and we are going to write about them. Now, normally, see here, you have got poset P and poset Q. If you have a function from P to Q, then it can preserve order. Yeah, if P1 is less equal P2, then f of P1 is less equal f of P2, preserve order. If f of P1 is less equal f of P2, then you can ask that P1 is less equal P2. What do we call it? Reflects order. Now, there are similar such notions for limits. The third one is more interesting. Yeah, so let me talk about that later. So, say that a functor f from C to D preserves limits, and I'm always going to talk about of shape J. If for any diagram D from J to C, yeah, and given and a limit cone. So limit cone is L to, let me call it theta sub j to dj, where j is in objects of j. Just to brush up your memory, what is L called in this cone? What is the technical term for L? Summit. And what are theta j's called? Legs. Okay, and the limit cone this for D. The cone, what will be the preservation property? If it comes from you, it's always better. What should be the preservation property? That you take the image of this cone inside category D. That still remains a limit cone, a terminal object, correct. The cone FL to FDJ, and this should be f theta j, j in objects of j, is a limit cone for what? For which diagram? No. Limit cone is never for the shape. Limit cone is always for a diagram. So which diagram? FD, correct. Okay, so preserves limits. Simple thing. We'll look at examples together, yeah, for all these three properties. So say that a functor f from C to D reflects limits of shape J if for any diagram D from J to C and a cone L to DJ, theta J, J in object J, for D, if its image, if the cone FL, F theta J, F dj, J in object J, is a limit cone for FD, then the original cone itself must be a limit cone for D. Then L theta J, dj, J in object J, is a limit cone for D. So you are given just any cone, then you take it further along F and that becomes a limit cone. Then you ask that, okay, if that is a limit cone, then my starting point must have been a limit cone itself. There are obviously some definitions like this for colimits. Preserves colimits, yeah, preserves reflects colimits. We are just going to do it for limits, but you should practice writing down the definitions for for colimits. Okay, now there is this last thing and I will tell you the name. So say that a functor f from C to D creates limits of shape J if for any diagram D from J to C. Okay, now here something is interesting. So create, as in we have no idea about anything happening in C. Something good happens in D, which means the limit cone will exist in D. But that limit cone, the summit of that limit cone, need not be in the image of capital F. But what we ask, that no, there should be a lift. Yeah, there should be a lift, as in there should be a particular cone in the original category which maps to that. Well, maps to that is a bit strong statement. In category theory, we shouldn't really do this. Yeah, it maps to that like perfectly. We don't know a priori whether that summit of the cone is in the image. But what we require, it should be isomorphic. Yeah, that cone should be isomorphic to something in the image. And moreover, yeah, the last property is important. Let me finish writing this part and then we'll see last property. Okay. Given diagram this and a limit cone M mu j f dj, J in object J, for Fd. Directly we have data for Fd, yeah, nothing for D. There exists a cone L theta j dj j in object j such that for d such that its image like fl to fdj, f theta j, j in object j is isomorphic to the limit cone, the given limit cone, and moreover any such cone is a limit cone for D. This last condition is extremely crucial. So what we are saying that anything, any cone over D that maps isomorphically to the limit cone over FD, then any such cone should be a limit cone. Yeah, we are immediately going to look at some examples and then you will see what I'm trying to say here. So for example, now, well, whenever we start with examples, always forgetful functors are the nicest examples. So U from GR to sets. Okay, does it preserve limits? Does it preserve products, let's say? What is the product of two groups? Cartesian product. So Cartesian product, will it preserve product? Yeah? Good. Then, what more? It preserves products, it preserves equalizers. How did we construct equalizers? Recall in the category of groups. Right. So preserves limits and also creates limits. See, basically what we are saying that any limit that you want to construct in the category of groups, you first construct it set theoretically and then it automatically gets an induced group structure from the diagram. That is what the meaning of create is. You don't have to do any extra work. It actually lifts, yeah? I mean, in this case, you can actually have a strict lifting. If you read Macaulain's book, then it's written there that you need this cone in the definition of creates limits, yeah? You need this cone L to dj, L theta j, to map directly to M fdj, M mu j. Yeah, we are not, there it's not said that it should map isomorphically. It requires you to map it up to equality. But we are taking this weaker definition slightly, more relaxed. But in this case, it actually creates limits. However, recall what is the co-product of Z and Z, two copies of Z in the category of groups. Free product. Now, does that mean that this forgetful functor actually preserves co-products? Free product is too large, yeah, compared to the underlying set. So therefore, it preserves this but does not preserve co-products. You can actually write lot of things. Yeah, like this. You have multiple You take an example of a functor and then ask all these properties. What particular limits does this functor preserve? What particular limits or co-limits it reflects and creates? Yeah, this is an open playground, and I want you to play with such ideas. Yeah, however, it will preserve directed co-limits. Yeah, if you care about them enough. If you work with category theory for long enough, then the most important co-limits you will care about are directed co-limits. Yeah, okay. So what about, let's do the same thing with top and sets. So what happens? Will it preserve something? It will preserve all limits. Okay, so this functor u from top to sets, it preserves limits and co-limits. Okay. By this I mean all small limits and co-limits. But it doesn't create products or any, but it doesn't create or reflect them. Okay, for example, if you take x cross y with discrete topology where x and y are topological spaces, then you know that with respect to discrete topology, any map with domain discrete is always continuous. So therefore, this is definitely a cone over two element discrete diagram x and y, two object discrete diagram. And if you think about reflection, then take u of this, what will it map to? It will map to a product diagram in the category of sets. However, yeah, this diagram is not a product. What should be the product diagram in the category of topological spaces? The topology on x cross y should be the product topology. So therefore it doesn't reflect. Similarly, it doesn't create them either, because this is the last line which I said is important, yeah, that any such cone which maps isomorphically to a limit cone must be a limit cone itself. Yeah, this last line, that there is a cone such that this is isomorphic to the given limit cone, and any such cone is a limit cone. So there are multiple such with product topology as well as with discrete topology. Both of them will map to the product, the limit cone. So it can't create. So you understand like what we are saying? I mean, we are saying something very profound about standard mathematical object, but it's being written in a very abstract language. Okay. So I'm not going to spend any more time with these concepts. Yeah, you should play around with these concepts. Yeah, take any functor and ask what you can do. However, now we will go through something else, and we still want to talk about limits and co-limits, but this is a very interesting property, like even undergraduates can understand this. Suppose you are given, yeah, I mean, I'm going to write down this problem properly. So suppose X is a set, then what algebraic structure does the set of functions from X to R can be equipped with? You understand this question? Set of all functions from x to r. X doesn't have any structure, yeah, x is plain set. But real numbers have lot of algebraic structure. It has got what algebra structure? Pointwise addition, pointwise multiplication, then pointwise 0, pointwise 1. So basically, because r plus 0 is a group, so functions from x to r, that also becomes a group. It also becomes an abelian group. It also becomes a ring. It also becomes a vector space. So x doesn't need to have any structure. It just comes from the codomain. Okay? So the same thing we can say about categories. That if the codomain category has lot of structure, then the functor category has lot of structure. Okay, so that's our next theorem. Okay, suppose D has limits of shape J we always do it locally, yeah, limits of shape J, but you can do it globally also. Suppose D has limits, all limits, then you can continue. Then for any category C, the functor category CD has limits of shape J and the evaluation functors F mapping to FA from CD to D for A in object of C, preserve them. Okay, you understand that if D has a lot of structure, then CD also has the same structure, and the evaluation maps preserve them. We are actually going to use this property to construct these limits. Yeah, that the evaluation, I mean, this is not a property, we'll slowly build this up. The proof is going to be technical, but before we go to the proof, let's discuss the ideas that are involved. What should we start with? We should always start with a, you want to show it has limit of a certain shape. Cone, directly cone. You should first be given a diagram. Okay, a diagram in the functor category. Yeah, we are again going to call it D. So that's why I always separate this D with category D. Okay, so a diagram is given. Then you want to construct a limit over that diagram. It's not directly possible. However, if you compose it with the evaluation functor, then you land inside category D, which has limits of shape J. So therefore, you can construct limits there individually. For every object, you can construct limits. So you will get, for any object A, you will get LA as an object. And now you have to use the data of LAs and their universal property to also construct image of morphisms under L. Because for each object A of category C, we have got an object LA of category D. But we should also have, for any morphism A to B in category C, you should have a morphism from LA to LB in category D. And once you have all such data, then collectively that will form a cone over original category, original diagram D. And once you obtain a cone, then you have to show it is a limit cone. Okay, so it's a multi-step process. Let's start with that. So let D from J to CD be a diagram. Let DA from J to CD to D be the composition functors. Composition functors. Yeah, where what is this second functor? It's evaluation at A. Yeah, F maps to F sub A. So what is DA? DA is, sorry, F maps to FA, not F sub A. You know the first one is given to you. The second one, we have already discussed what it is. Okay, be the composition functors with limit cones LA. What should I write? I will use lambda JA to DJA, where J is an object of J. Okay, so little j is an object of J, that should always be the index of legs. D of J is a functor. Yeah, D of J is a functor from C to D, and we are evaluating it at A to get an object of D, category D. So that's how we are writing. Yeah, and LA is just the name of the summit. Right now it doesn't mean anything. We have assigned it the name LA. Yeah, and I'm choosing a limit cone always with limit cone this. What is A here? A is an object of, A is always an object of C. So for each object of C, I have a limit cone over which diagram? D sub A. And what is D sub A? It is the composition of original diagram D with the evaluation functor at A. Okay, so now what should we do? This is just the object to object assignment. We started with some A and I got some LA. A was from C, LA is from D. I got that. But now I should do morphism to morphism. Okay. So, yeah.
When we evaluate at A, so we set F to Fa, and we set any natural transformation from F to G to its coordinate at A.
Yeah, it's just an evaluation functor. So, yeah, correct. Whatever is the natural choice.
So, how do we know that this LA is the limit?
How do we know that LA is the limit? No, it's given that D has limits of shape J. So I know existence of limits in category D.
Yeah, but how do we know that? It is in the it is in the image of F.
It is in the image of F. No, it doesn't matter. See, what I did, so we started with a diagram in the functor category. So what are the objects in that diagram? They are all functors. I evaluated each functor at object A.
Yeah. So I'm saying that these DJAs would be like objects in D.
Objects in D, correct?
And then we'll get a limit which is an object in D
object in D, and I'm calling that summit as LA.
How do we know that there exists an L such that LA is
No, no, LA is the name given to the summit.
so but L is a morphism in CD, right?
No, no, L is not a morphism in CD at all.
Oh, L.
L has no meaning so far. I have just said it's LA. Yeah, up to isomorphism, I can always do that. If you remember, then the proof for equivalence of categories that we did something similar. Yeah, if F is part of an equivalence of categories, sorry, the fully faithful, essentially surjective functor. Yeah, we always construct it like this. Yeah, same thing. LA is just the name. I'm going to construct a functor L out of this data. Okay, so given F from A to B in C, now I need to show something. So we are going to, okay, ultimately we are going to use this diagram. I will keep that diagram aside, but we have to justify a lot of things before that. So we have djb, okay, then we have dja. So from dja to djb, do we have a map? What is it? djf, correct. And from LA to dja, I do have a map which is lambda j comma a. Yeah, that's what we are writing for this. And from LB to djb also I have a map. I call it lambda j comma b. Okay, if I can show that while starting with this top one, A, I have a cone over the original diagram. So what is the base diagram here? It's dB, d sub b. If over d sub b, I have a cone whose summit is LA. Yeah, I do have some legs. I have to show that it forms a cone. If I can show that it forms a cone, then it will factor through the limit cone. And the limit cone has summit LB. And that factorization is always unique through the limit cone. So in that case, I will get a unique morphism from LA to LB, and that is what I will denote by LF. You understand this? No. See, I have D sub B at the base. D sub B is a diagram in category D. Okay. D sub B is a diagram in category B, and I know the limit cone over that. What is the summit of that limit cone? LB. LB. And what are the legs of that cone? Lambda JB. Okay, if I can construct another cone, then the limit cone is terminal. So I will show that there is another cone with summit LA. And then because there is another cone, there will exist a unique factorization through the summit of the limit cone, namely LB. And that unique factorization I will call as LF. So that's how I am constructing my functor L. Okay. So given F from A to B in C, now I need to show something. We will argue that whatever I have shown in the diagram, yeah, these compositions LA to dja to djb, this is djf and this is lambda ja, j in object J, is a cone over D sub B. If we can show that, so that there is a unique factorization of this cone through the limit cone, i.e. LF from LA to LB. Okay. Now I have to write a proof of this. Yeah, it's not yet complete. So proof of this cone over dB.
It is a composition of two natural transformations.
It's a composition of what is a natural transformation? Lambda sub JA is not a natural transformation yet.
No, it is a natural. Like the datum lambda sub j is for
Uh-huh.
j in capital J.
Huh.
It is a natural transformation between diagrams interpreted as functors. LA being the diagram at LA.
LA is the diagram.
Yeah, you introduced limits as cones as natural transformations between diagrams.
Uh-huh.
So a cone is a natural transformation from a diagram whose image is a single object and all the morphisms are identity to a diagram. That is a cone.
Okay.
So the first part is a natural transformation.
How is lambda JA a natural transformation? Like in A, LA to DJA.
So when you collect all these morphisms, lambda j
Huh.
for j in capital J, so that is a natural transformation from the diagram which ends up at LA and the diagram dj blank. Sorry, d blank A.
D blank A. Okay, we'll do it directly, then we will talk later. So how do we show that? Like for any morphism in the original diagram, so in the original shape category, so given alpha from J1 to J2 in J, in morphisms of J, yeah, what do we know? We need to show this D alpha B D J1 F lambda J1 A equal to D J2 F lambda J2 A. This is what we need to show. What we have done, we took the first leg, then covered a morphism in the image that is same as directly covering the leg for that particular object. Is this clear? Yeah, look at this. These are the two different legs of that diagram. And this is the morphism. This curly morphism is the morphism that is covered in the diagram. So we have to show this. So what will be this left hand side? Well, for that we will need some diagram. Yeah, and I'll use that D is a functor dj. Yeah, okay. Let me draw that diagram as an aside over here. I can directly write this, but I tried to make life simple for the audience. So dj1a, and here I have dj1b. Then What is the map from dj1a to dj1b? You tell me.
D alpha, sorry,
dj1,
DJ1F.
dj1f. Okay. What will be the vertical one? Obviously, I am changing j2, j1 to j2, and I am keeping a. What are the vertical maps? D alpha a. And this is the same thing, dj2b, and this is dj2f, and this is d alpha b. Okay, so this diagram commutes, and therefore what is this particular side? Well, we have d alpha b composed with dj1f, which is one side of this commutative square. I have to replace it with another side. So I will write dj2f composed with d alpha a, then lambda j1a. And can you see why this is true? Because this underlying part, d alpha a, lambda j1a, this underlying part is lambda j2a. Why is that the case? As Suyash already said, yeah, why is that the case? Because something is a cone. What is a cone? The original limit diagram has that cone property.
This is a natural transformations from one diagram to another diagram. So this has to be.
No, see, LA to DJA, lambda JA, that was a limit cone. So in particular, it was a cone. So therefore, I went from LA to DJ1A and LA to DJ2A, and inside the diagram, I am moving along D alpha A. So that diagram commutes. So that's why this second property is true. Okay, so that's how this commutation, we wanted the horizontal one, but we went via this. And that's the reason why it forms a cone over dB. Once it forms a cone over dB, I already said that there will exist LF from LA to LB. Okay, any questions over there? So we obtained a morphism which we called LF. Yeah, again, it's a name given to LF. Okay, so now I'm just going to write something which you have to accept. So uniqueness of LF ensures that L is a functor in CD and lambda j from L to dj is a natural transformation. So Suyash, were you talking about this particular natural transformation, which we just proved? Okay, so lambda j from L to dj is a natural transformation. All these things are now straightforward. Yeah, because now if you have LA to LB and LB to LC, then it should do exactly the thing that you want. The composition should do the thing that you want. So therefore, composition is also preserved. Identities are preserved. Everything works because of uniqueness of this factorization. Yeah, so very beautiful way of obtaining a functoriality via factorizations. Furthermore, what are the components? Yeah, we are saying lambda j from L to dj is a natural transformation. What are the components of this diagram? I mean components as in components of this natural transformation, lambda j sub a. Yeah, that's how we write the components, alpha sub a. Yeah, so right. Now, Now what do we start with part 2 of the proof. Yeah, so clearly L to dj lambda j, j in j is a cone over D. Why is it true? Why is it a cone over D? You have to check this property, okay? I will give you what you want to check. If you have dj1 and you have dj2, then this is lambda j1, this is lambda j2, and whenever there is a morphism alpha, then this should be d alpha. Why does this diagram commute? Where is this diagram first of all? In which category am I drawing this diagram? This commutative diagram?
This is in the
CD category, correct, functor category. All of these are natural transformations. Even though I am writing them as arrows, they are natural transformations. And this diagram does commute because of uniqueness, exactly. So therefore, this is a cone over D. Okay. Now we have to show that given any cone, let me say f to dj and theta j, where j is an object of G, over D. Okay, what do we have? So this is a cone, any arbitrary cone. We need to obtain a factorization of any arbitrary cone through the original cone, the limit cone, because then only we can prove it's a limit cone. But we can't directly do it. We have to first go to the category D, yeah, via evaluation functors, or by simply taking the component. So given any cone f theta j over D, yeah, what do we get? Well, I'm just going to draw another diagram over here. The eighth component of this particular natural transformation is from here to here. Yeah, that's theta j. Maybe I should draw it a bit vertically so that you can understand what's happening. So this is FA and this is my dja. This is a morphism in the category D, theta ja. Similarly, I have LA and I have lambda ja. And FA to LA, what do I have? There exists a unique factorization because it's a limit cone. Yeah, what do you need to show? There is still something to show. But because this is a cone over D, its composition with the evaluation functor is also a cone. And therefore, you can get a factorization through the limit cone over the composed diagram. So therefore there will exist a unique functor, let me call it theta sub A, such that this diagram commutes. Yeah, so given any cone, we have this particular factorization, and hence a unique theta A from FA to LA for A in objects of C. Now this is the data that we needed. So for each A we have a morphism FA to LA. What does that mean? If it satisfies certain commutative squares, then this becomes a natural transformation. So such that, let me also write that lambda Ja composed with theta A is equal to theta Ja. So therefore, I mean this is happening for all J in objects of J. Therefore, theta A in objects of C forms a natural transformation, forms the data of a natural transformation. Okay, so because this is the data of a natural transformation and we get this natural transformation by uniqueness of factorization through limits. And this is the, maybe I should write one more line. Since theta A are unique, yeah. Okay, so this theta is the required factorization of f comma theta j through L comma lambda j. I guess some of you have already given up, you are just copying. See, the proof is not hard. The idea is very simple, that you are given some cone, you only know one thing to do, you do that thing, but there is a lot of technical verification involved here, like where exactly is this diagram? Okay, so I'm going to give you one very simple application of this limit business and preservation, yeah, that you will enjoy, I'm sure. So, f from A to B in any category, yeah, I mean, maybe I shouldn't use the notation, is a mono if and only if, yeah, the pullback of f along itself is identity. So A to B, FF, and this is A, identity, is a pullback diagram. Okay, so this is an important observation. Dually, what will you have? This is an AP if and only if identity comma identity will form the push out diagram. Okay, so therefore, if it has very interesting consequences. Therefore, if f from C to D preserves pullbacks and C has pullbacks, yeah, I mean I should have written this first, that C has pullbacks and f from C to D preserves pullbacks, then f also preserves monomorphisms. Okay, so a criterion for testing whether monomorphisms are preserved. And there is another, like maybe I will call this one, second one. Yeah, this one you have to do a little bit of work. Okay, so the second application of this fact is that if D has pullbacks, then alpha from F to G in the functor category is mono if and only if each of its components is mono. Okay, so natural isomorphisms, you have already seen the statement. It's always true. It's a natural isomorphism if and only if each component is an isomorphism. Now this is a corresponding statement for monomorphisms. Right. Any questions so far? So the one interesting question is, can we find some common property of all the functors which preserve limits? All limits which are present in C, we want a common property for all such things. They should be preserved, yeah? And the answer lies in a very interesting new concept that we are going to study. But before even uttering the word, let me give you some examples. Yeah, so all of you have seen topological spaces. What is topology? What is an open set? Collection of subsets of power sets, okay. So, and similarly closed sets are also subsets of power sets, yeah. Like each closed set is a subset of the topological space. So suppose X is a topological space. I'm not going to write the x comma tau because this is not a topology class, but I will write something. Px is its power set. Cx is the set of closed subsets of X, and Ox is the set of open subsets of X. Okay, then I have something interesting happening here. Between Cx and Px, Cx definitely embeds inside Px. All closed subsets are subsets. And in the reverse direction, do I have a map from Px to Cx? Closure map. Okay, so this is inclusion and this is closure. Closure we usually write by bar. And what is the property? That if A is contained inside a closed set, I'm going to use letter F, yeah, the inclusion of F. This happens if and only if the closure of A is contained inside F. Yeah, so for any A in Px and F in Cx. Do you agree with this? A set is a subset of a closed set if and only if its closure is also a subset of that same set. Dually, we have something for open sets also. Yeah, we have open sets and the whole set of subsets. This is also inclusion. And from power set to Ox, what map do we have? Interior map. Okay. Okay, so let me start with any A over here and any U over here. Then what can I say? It should be the dual property. So I will say that U is contained inside set A if and only if U is contained in the interior of A. I will write just to highlight that the inclusion of U in the power set is contained inside A. Well, IU and U are not different, but they are just elements of different posets. Okay, so IU is a subset of A if and only if U is contained inside A interior. Now, if I write the same thing down in home language, so home is non-empty on one side if and only if home is non-empty on the other side. So let me write that. So in Px, Px without brackets. So Px IU comma A is non-empty if and only if in OX U comma A interior is non-empty. Now either this home set can be empty or singleton. So when I'm saying that this is non-empty if and only if the other side is non-empty, I'm actually saying there is a bijection between these two sides. Okay, because one side is singleton if and only if the other side is singleton, then similarly one side is empty if and only if the other side is empty. So therefore we have this bijection. Similarly for closed sets and power set also will have a bijection. And what is happening, that there is a functor. I is a functor, yeah, I is inclusion map, it's a inclusion map of posets, it's a monotone map, and similarly interior is a monotone map. Both of them are monotone maps, so therefore they are functors. So one functor I is changing the comma and it is becoming interior on the other side. It's just crossing the comma and it becomes a different functor. So this phenomenon is called adjoint functors, adjoint pair of functors. I and interior, inclusion and interior are adjoints of each other. Inclusion is the left adjoint, interior is the right adjoint, because inclusion appears on the left of the comma and interior appears on the right of comma, and we write it like this, that I is a left adjoint of the interior functor. What can you say about this one, the closure and inclusion? It's the opposite way around, yeah, that the closure functor is a left adjoint of the inclusion in this particular situation. Now let me give you this definition of this concept, and this is again one of the most important concepts in category theory. So adjunctions, they were introduced by Kahn in 1958. I'm surprised why people didn't see them earlier, because now people say that adjunctions are ubiquitous in mathematics. Ubiquitous, omnipresent, they are present everywhere, and you will see how they are present everywhere. Okay, so what we want, yeah, a pair of functors CD, F is here, is said to be an adjoint pair of functors if for any A which is an object of C and B which is an object of D, there is a natural bijection I'm just going to call natural bijection phi AB from DFAB to CAGB. So you can observe that F crosses the comma. Of course, you land in a different category, but then it becomes G. A and B have their fixed location, and you always have to write categories appropriately. There is a natural bijection, naturality in both A and B. Okay, I can tell you what naturality is in two different ways once again. Yeah, first one is simple, like we are talking about home functors ultimately. Yeah, so if C and D are locally small, then naturality in A and B is an isomorphism, is a natural isomorphism between the following functors, following parallel functors. First one, you start with, it's always covariant in one component and contravariant in another. So which, for home set, which one is contravariant? First one. Okay, so I'm going to start with C op cross D. Okay, the first one is simple, it's C op cross C, and then I land inside sets. And the second one is also simple. I go inside D op cross D, and then I land inside sets. So tell me the name of the functor from C op cross C to sets, this bifunctor. It's the home in C. That's the only thing you can do. C blank blank. This is D blank blank. And over here, C op is being preserved, so you will say 1 sub C op, and cross, what will you do from D to C? You will go via G. From D to C you can go via G. And from C op to D op, what can you do? F op. And cross identity on D. Okay, so this is a natural transformation between these two. But what does naturality really mean? Naturality means that the choice of bijections is natural. Otherwise, you will have to choose it individually for every pair of objects. But they should be compatible with the categorical structure that we already have. So naturality in simple words, yeah. So let me do naturality in B, you can do naturality in A similarly. It will be contravariant, yeah, remember that. So we have D, F, A, B and C, A, G, B. Okay, this is phi AB. Naturality in B refers to if I am given a map from B to B prime, then I have FAB prime and phi AB prime over here and CAGB prime. This is another bijection, phi AB prime. How is it related to phi AB? Well, I have the only thing I can do, if I have a map from FA to B, I can compose it with G, and on the other side I can compose it with GG. So this diagram commutes. That is naturality in B. Similarly, you will have naturality in A, it will be contravariant. I mean, ideally I should finish here, but it's not fun if I don't give you any examples. So I'll give you a couple of examples and we'll continue next time with more examples. So examples in green. So obviously from groups to sets, We have all looked at this. You always need to look for example like pair of functors in opposite direction. From groups to sets, you always know what it is. Forgetful functor. In the opposite direction, do you know any functor? Free group functor. Very good. So let me call it F. Then are you convinced that free group functor is the left adjoint to the forgetful functor? What do I mean? So I start with a set X, yeah, and then I take the free group on X and G, and this is happening inside the category of groups. And on the other hand, I am working inside sets from X to the underlying set of group G. Okay, tell me the universal property of the free group. It's free in the sense that the image from fx, like image is determined by the image on the generators, x. So any function from x to g is going to naturally extend to a group homomorphism from fx to g. That's precisely this bijection is, and that's a natural bijection in both x and g. Yeah, you will have more such examples, but perhaps I should stop here for today.